the next topic is MOSFET, metal oxide semiconductor field effect transistor. So this is the improved version of field effect transistor. Here we don't have any PN junction structures. Instead the gate of the MOSFET is insulated with from the channel by a SiO2 layer. So SiO2 layer is an insulating layer. Basically, whenever we use SiO2 layer, silicon dioxide layer, it will be a semiconductor. It will be an insulating layer. So this is since it is having an insulated gate, because as we told, SiO2 layer is present with the gate. So since it is an insulated gate, we call it as insulated gate field effect transistor, IGFETs. Instead of MOSFET, they can even ask you what is IGFETs. So IGFET is nothing but MOSFETs only. It is insulated gate field effect transistor, whereas MOSFET is metal oxide semiconductor field effect transistor. Metal oxide because we are using silicon dioxide layer. It is an oxide layer, so that's why we are using the term oxide in the name. So in this there are two types: depletion MOSFET, enhancement MOSFET. So depletion MOSFET is taken as D MOSFET, and enhancement MOSFET we call in short E MOSFET. Again, this depletion MOSFET is classified into two types: N channel D MOSFET, P channel D MOSFET. Again, this enhancement MOSFET is classified into two types: N channel E MOSFET, P channel E MOSFET. So we'll study one by one. And in this, among these two, depletion or enhancement, one question is compulsory: construction and working. And it is the construction and the working of these MOSFETs are entirely different from FETs, JFETs, junction field effect transistor. The way they were working is entirely different from how these MOSFETs are working. So coming first, we'll start with a comparison. First, we'll know what are the difference between those two. So later on, we'll start with the actual things. So in the comparison between JFET and MOSFET, so JFET is fabricated using a semiconductor bar, which acts as a channel. So we had taken a N-type layer, right? N-type layer. After that, we used to diffuse two P-types on the either sides. And after that, we are calling that N-type layer itself is a channel, which is allowing the electrons or the charges to flow from the source to the drain. But here in the MOSFET is fabricated on the semiconductor substrate. We take a substrate means a separate layer we take. On that we are going to fabricate this one. So here on the bar, semiconductor bar we used to take, on that only we are going to embed, and whatever we want to do we were directly doing on the semiconductor bar. But here we take a separate substrate. A substrate is just like some base, separate base on which you are going to build something. Okay, so that kind of fabrication is said to be the substrate oriented fabrication. So fabrication process is complex here, but the fabrication process is simple here. Say here the fabrication process in the JFET is complex because we have to take an semiconductor bar and we have to embed two P types on the either sides. So after taking that, we have to embed, we have to diffuse it and make it as P type. That is a bit complex process. But here in MOSFET, what we are doing, I was just telling, no, we take a base, on that we are going to add one more layer, on that we are going to add one more layer. It is just like putting a foundation to the one while building the house. We put a foundation, on that we'll have a walls, on that we'll be having the roof. It is like that, one by step we'll be growing. But here it is just like taking a stone, a big stone, and you are going to just make some holes or anything. So I'm just giving you an analogy. So how much complex it is to drill a stone, and how much it is easy to build, and if you are going for a step-by-step building process. So JFET does not contain an insulating silicon dioxide layer. So it is not having that silicon dioxide layer. So SiO2 layer is absent here. So we don't have any insulating layer in JFET. But here it is having SiO2 layer, and it is acting like one of the major layer in the MOSFET construction. So JFETs are operated in depletion mode only. So it will be operated in depletion mode. Depletion mode means you have seen that the P and N type, they will be always reverse biased. The gate is always reverse biased, and by making them reverse bias only, we are going to work. We never forward bias them, and we'll work on it, right? So but here we are having two modes of operation. One is depletion mode, other one is enhancement mode. Both modes are available here. So JFETs have larger drain resistance in the range of 100 kilo ohm to 1 mega ohm, but MOSFET has lower drain resistance of the range 1 kilo ohm to 50 kilo ohm. So this is the range we are having here, and this is the range we are having here. So you can just imagine it is having 1 mega ohm and it is having 50 kilo ohm range. And coming to this input resistance means the gate resistance. So it will be are lesser in the range 1 giga ohm to 10 giga ohm. So that it might be in that range. So coming to this one, the input resistance offered by MOSFETs are much higher in the range of 10 to the power of 13 ohm to 10 to the power of 15 ohm. So it is in the giga range, and this is in terms of 10 to the power of 13 to 10 to the power of 15. Okay. So the leakage current is more in JFETs in the range of 10 nanoamperes to 100 microampere. So there will be some leakage currents, which will be because of the leakage currents, in the sense some currents might flow towards the gate because by penetrating it through the depletion layer. So that is the leakage current. So leakage current is much lesser in MOSFET in the range 10 picoamperes to 100 nanoamperes. See, as there is no concept of PN junction in this case, obviously the leakage current will be lesser in MOSFET compared to the JFET. But here we know that the gate is mainly working on the concept of PN junction gate. We create a PN junction, and by reverse biasing that, we are going to uh, conduct. We are going to do it. So next, JFETs are not so widely used in electronic and computer industries. So MOSFETs are extensively used in digital electronics and computer industries. So MOSFETs are extensively used, but whereas JFETs are not that much widely used. So next, after this, these are the differences. This is also important from the point of examination. They'll be asking the compare JFET and MOSFET, or tell me list out some differences between JFET and MOSFET. So you have to know this one. Like this, even we have given the difference between BJT and JFET. So you should know all these differences. Depletion MOSFET, that is D MOSFET. So depletion MOSFET, in this the depletion MOSFET, we are going first, will study N channel D MOSFET. So in the N channel D MOSFET, the construction is like this. So as I told, they will be taking a substrate, separate layer, separate base they are going to take. So here we take a P-type substrate. So substrate means it is not having any, it is not going to take part in any conduction process. It is nowhere concerned with the movement of charges or anything. So it is not going to disturb anything. So it is just a base which we are taking, P-type substrate. P-type substrate means it is containing majority charge carriers as holes. Okay, and this is just a ohmic contact or a metallic contact through which we are having substrate connection. So to, in order to have any connection to this, we can give. Suppose sometimes we don't want even the holes to if the holes are trying to penetrate or some electrons are trying to penetrate and we don't want to happen such during that time, we can connect it to some particular supply, negative supply or positive supply if required. But 99.99% cases, this substrate connection will be left open. They will provide the substrate connection, but will not use the connection. It will be always open. It remain open always. So after taking the substrate connection, what they will do is they will take this. This is N type. They are going to put this much part diffuse N type material here, and they are going to take one more N type layer here. So two N types are constructed. Here one N type and here one N type they are going to take. So in between these two, what they are going to do is in order to connect these two, this is taken as the source, this is taken as the drain. In order to connect these two, we are going to take one more N layer. This N layer is going to connect this source to this drain. Okay, a thin layer which is been connecting this source to the drain is known as N channel. So because this is the path for the electrons to flow from, if as I have told, this is our source and this is our drain. So this is the path for the charges to flow from source to the drain. So since this is considered as path, we call this as a N channel. And this is having since we are taking N type material to connect these two, we call it as N channel. Okay, why we have taken N channel only is because here also we have N type material, here also we have N type material. So here the charges that take part in conduction process is electrons. So there will be flow of the current will be because of flow of electrons. So in order to make the electrons to flow easily, we have to take N type material only. So in N type material, it can easily flow and it can reach the drain. If we take P type material, then it might act like opposition to the flow of the charges. Again, your PN junction concept will come here. So that's why, to overcome that drawback, what we have done is we have connected these two N type with the same N layer. After that, what they have done is, see, you can see here the shaded part. This part is with the shaded with lines. This is our SiO2 layer. So they put one SiO2 layer, and you can observe one thing. This source is directly connected. This is a ohmic contact. Ohmic contact means the metallic contacts. This is also metallic contact. This is also metallic contact. You can observe here, these metallic contacts are in direct connection with this N layer. Well, we can call it as a well. Okay, it looks like a well, no? So we can call it as N well. So this metallic contact is in contact with the N well. This metallic contact is in contact with this N well. But see this metallic contact, this is not having any connection with this N channel. So there is no connection between these two. So they are insulated. Between these two, there is an insulating layer. So this metallic contact is not in contact with this N channel, but this source is in contact with this metallic contact. This drain is in contact with this metallic contact. And this is our SiO2 layer. And we take this as the source, this as the gate, and this as the drain. Okay, I'll tell it again. First, we'll take a P-type substrate and we will take two N wells, two N-type materials in this form, and we are going to diffuse it here. So we create one N well here, one N well here. The first one acts as, and this will be heavily doped, it will be moderately doped. And this will be this will act as source, this will act as drain. So in order to have connection between these two, we'll add one layer of N layer. So this N layer will act as channel or the path for the electrons to flow from source to the drain. So since we are using N channel to connect them, this type of MOSFET is known as N channel MOSFET. So the name given here is mainly because on the basis of the MOSFET. So N channel MOSFET. So it is the connection. It is the channel which is connecting the two, the source and the drain. So since it is N channel, it is known as N channel MOSFET. After that, we are having an SiO2 layer, and we have the metallic contacts, which are the source, which is in direct connection with the source, and this is one more metallic contact, which is in direct contact with the N layer. And after that, we are having the gate layer. So the gate layer is not having any contact with this channel. So that's why it is separate. So now after this, this is the construction. Okay. So this after the construction, we'll go for operation. How it will operate. See now, what we are going to do is, in the initial case, we will short the gate and the source to the ground. We are shorting the gate and the source, both are shorted and connected to the ground. Okay, and you can see the drain is connected to the battery, positive battery, and the negative terminal is connected to the ground, and the substrate is also connected to the ground. See, always remember, whenever you are going to connect like this two or more wires to a particular point, then we call it as a common point. Okay, that is a common point. So now this acts as a ground. If your negative terminal is given to this one, it acts as a ground terminal. Okay, now here what happens is, since as I have told in the earlier case, this is having majority charge carriers, the electrons, it is heavily doped. So now, and this is very moderately doped. So this was connected to the plus VDD, that is positive voltage, right? So when positive voltage is connected to this particular metallic contact, what happens during that time? Here, a kind of positive electric field is created, or positive voltage is created at this point. When a positive voltage is created at this point, what happens? Since the electrons are negative, it this electric field creates a kind of attraction for the electrons at this layer. So when this layer is been creating an attraction, because when this is connected to the positive, automatically this metallic contact becomes positive. Then this region acts as a positive electric field. The positive field will be created here. Because of that, electrons get attracted and they start moving towards this, where that constitutes the drain current. Okay. Again, because of this attraction, what happens? Some more electrons starts flowing. Some more electrons starts flowing. So here, whatever the electrons were there, they also get attracted and they also starts flowing towards this. Because of this movement of these electrons, what happens? There will be some amount of current which will be flowing in this drain circuit. So this constitutes current. But now, if suppose in the, I think I have not given that there. So if suppose if I'm going to connect this gate terminal, I'm going to connect it to some other voltage. Let us take, I'm going to connect even this gate terminal to some positive voltage, positive supply. The gate is connected to the positive supply, and source is as usual, it is grounded, but only this gate is connected to the positive supply. So when the gate is connected to positive supply, so here, since it is insulated, the electrons or any charges cannot penetrate here, or it cannot give any charges here. But what it can do is, it can create a kind of electric field here, some kind of electric positive or negative electric field around here. Okay, it can just create the field, or it can just create an attractive or repulsive force there, but it cannot add, or it cannot take out any charges, because the charges cannot penetrate through this insulating layer. It can just create an attractive or repulsive force across this layer. Now what I'm going to do is, I'm going to connect this gate terminal to the positive power supply. When I connect this to positive power supply, now what happens at this particular layer under the gate layer, this layer below the gate, so the kind of positive electric field is produced. When positive electric field is produced, what happens is, just look into this diagram. Already the electrons are flowing. Along with that, what happens is, since I told this is a p-type substrate, in p-type substrate, the majority charge carriers are holes. Minority charge carriers are electrons. That means, even though this is p-type material, it contains some electrons in it. When you are going to create a positive electric field here or a positive attractive force here, during that time, the electrons which are present in this and which were behaving like minority charge carriers in this field, they get into this channel. They get into this channel because of the attraction which is created by this gate terminal. Since it is creating some attraction, the electrons which are present in the p substrate that get into this channel. When they get into this channel, automatically what happens, the electrons which were already flowing, no, that electrons will also add up these electrons together. So because of that, there will be rays of current. So already let us assume in this channel, so there are 100 electrons which are flowing. So when minority charge, some 10 minority charge carriers were here. So when the 10 minority charge carriers jump into this n channel, now what happened? 100 plus 10, 110. So what happened now? The number of charges which are flowing from the source to the drain, source to the drain is still increasing. So because when the number of charges are increasing, automatically the current flow from source to the drain also increased. Okay, and this is known as enhancement mode of operation. This is known as enhancement mode of operation. Why it is called enhancement mode of operation is, see, we are enhancing the number of electrons. We are enhancing the number of electrons to the in the channel. Suppose if I'm going to give negative electric field or negative potential to the gate. So during that time, what will happen? During that time, this the when we provide a negative electric field, a negative potential here, during that time the electrons which were moving here, these electrons which were moving here, they get deflected to the p substrate. When they get deflected to the p substrate, automatically what happens, the flow of charges from source to the drain decreases. So this is how we can control the flow of charges. Here the flow of charges from source to the drain is controlled by giving the opposite, giving the same voltage. See, electrons are negatively charged. If you give negative, what happens, the electrons which are flowing here, they get deflected. Instead of moving here, they get deflected into p substrate. So when they get deflected to p substrate, what happens, the number of electrons which are flowing to the drain starts decreasing. Okay, so this is what happens. Okay, so can anyone explain now, after listening to this much, can anyone explain how it will work? Let me see. Try in your own way. Just brief it out, not in detail, just how it works. No one. Tejaswini,
Yes, sir.
can you explain me how it works?
Um, okay, sir. There are two n-type
Hmm.
that are there in this, and between those two, there's another n layer, which is it's a thin channel, which is called as n channel.
Hmm.
And this n channel is the path for the flow of electrons,
Hmm.
and both the both the n
Hmm.
types are directly connected to the ohmic
Hmm.
contact but
mm,
the N channel is not
mm,
connected directly.
mm,
The drain is connected to the positive terminal of the battery,
mm,
and so the positive electric field is created at the N region that is connected to the terminal of positive terminal of the battery,
mm,
and all the electrons move towards the positive electric field.
mm,
Then, when the gate is connected to the positive of the supply and when it is not grounded, that time
mm,
a
mm.
positive electric field is produced near the gate.
Okay.
Then, the electrons present in the P substrate they
Mm,
move towards the electric field in the N channel, and
mm,
that's why there'll be like lots of electrons in the N channel, and
mm,
that will give rise to current.
mm.
This current is known as I mean, this process is known as enhancement mode of operation.
Okay, very good. So this is how it works. Now, if you have any doubt, if you have any doubt, you can ask me anybody. If you have any doubt, you can ask. If you want me to repeat any part, I can repeat. Okay, I think hope everyone has understood. So, how we are going to control this flow of charges is we are just going to apply that kind of voltage. See, if I want to increase the current, I'll apply the opposite voltage. If I want to decrease the current, I'll apply same kind of voltage here. If I want to decrease the flow of charges, what I'll do, I'll apply the same polarity. That means I'll apply negative voltage here. When I apply negative voltage, it creates a kind of repulsive force here. Because of that, the electrons gets repelled to the p substance. All these electrons gets repelled to the p substrate. So because of that, number of charges which are flowing to the drain start reduces. When you apply positive voltage during that time, what happens? The electrons which are present in the p substrate, they get added up to this n channel. Because of that, more amount of more amount of channel more amount of electrons will be increase, more number of electrons will be involved in the process of flowing, so that will be getting more drain current. So now in this this is about how it works. So again, here also we are having the transfer characteristics and drain characteristics. The drain characteristics is as same as what we have studied. It looks the same diagram. So, but we are having ohmic region and saturation region here. So this is the current, and this is the VDS voltage. So you know already what is ohmic region. It is a region where we can adjust the current and voltage of the MOSFET. And saturation region is the region where the current will be constant for a given gate to source voltage. So here gate to source voltage means whatever you will apply here, this gate voltage. You can observe here when it is 0 volt or whenever it is positive. So what has happened? More number of charges got into the channel. When this is positive, more number of electrons got into the channel. Because of that, we are having highest current. So when we are providing negative voltage, what happened during that time? See, the electrons were repelling from this channel to the p substrate. So that's why we were having lesser current. See, when you are increasing the in terms of negative voltage, the current is keep on decreasing. And finally, when VGS is equal to minus 6 volt, you will be having almost zero current. So coming to the transfer characteristics, we are having VGS versus ID. So in the VGS, again here, so we know since VGS, if it is negative, so you can see that at VP is minus 6 pinch of voltage. It is the minimum voltage after before which the current has to conduct, after which no current will start flowing. You can see that when negative gate to source voltages keep on decreasing, during that time the current is keep on increasing. You can see that at 0, VGS is equal to 0, you are having maximum current. But if you are going to still increase VGS in the positive direction, so you can see that this portion you can see the curve is still increasing. This is known as enhancement mode. So till that it was in depletion mode. Whatever the operation we have done from this point to this point, that is known as depletion mode. After that, whatever we are having, that is the enhancement mode. Enhancement mode because the electrons are added externally from the p substrate. So whatever the electrons which were present in the p well, not only that one, we added some more electrons. So that's why it is known as enhancement mode of operation. So this is the transfer and drain characteristics. So today I'll just take for half an hour. We'll end up now. So tomorrow I'll be continuing.